All right. Any questions before we get started today? No questions? All right, homework number 3 is due on Monday. That's also going to be a review session for the exam. If you have any specific questions that you want to review in that class, send an email to me describing what questions you want to go through. They can be homework problems, homeworks 1 through 3. They can be class problems. They can be something else, just general topics, but send those emails to me sooner rather than later. Yeah. So exam is going to be on through first order systems. It will not cover second order systems. Okay. And the exam, again, it's a week after Monday, so the 20th, and it'll be in person in this classroom, regular class time. It'll be for 45 minutes. All right. Any other questions? Guessing that's what you were going to ask.
Any notes or formulas given on the?
I will give you a Laplace table, like some common Laplace transforms. It will be open note and open book, I think. At least some form of open note and some form of open book, I would say. No calculators, no digital devices, nothing like that. We're going to go through this in more detail on Monday. All right, I don't want to have an entire class of just questions on the exam. So we are going to go through this in general. If it's really important, we could talk about it now.
It's not super important.
Okay.
Well, just can you say something about like cheat sheet?
That's I literally just said that, I think. Yeah. So again, we will cover that in detail. Yeah. Anything else? Yeah. There will be some form of open notes and stuff like that, right? Probably just entirely open notes. All right. Let's talk about the general second order system. That's our first topic for today. Then we're going to talk about underdamped systems specifically. All right. So we previously wrote our second order system as b squared over s squared plus as plus b squared, right? Now we're going to write it in terms of omega n or omega n squared here. S squared plus 2 zeta, that's supposed to be a zeta, but I don't draw it well. Omega n s plus omega n squared. We're going to focus on the case with no zeros. The numerator really doesn't matter too much at this stage. It will matter later on, but we're going to focus on that. So what are these new parameters, omega n and zeta? Can somebody tell me what one of them is? Natural frequency for omega n, right? Natural frequency for omega n. And I'm not looking for like a rigorous mathematical definition, but what is the natural frequency? Like more physically, let's say. What does it describe? Let's say if it's a mass spring damper system, what is natural frequency? Oscillation, something to do with frequency. Yeah, oscillation, something to do with that. Anything more? Oscillation for what circumstances, maybe? Right. I've noticed you say, I don't know if I'm sure about this, and then you say the right answer every time. So yes, it is the case if there's no damping, what the system would oscillate at, that frequency, right? Right, potential energy to kinetic energy exchanging those two, right? So that is the frequency of a system if there was no damping for that second order system, right? What's our other term here? I think I heard somebody whisper it before. What's that other parameter? All right, so what's our damping ratio, which I'm going to, again, I will tend to just make squiggles or I'll do something like this, but that's what I mean by zeta. It's not correct at all. I'll just say zeta. That's what it's supposed to be. All right. What is a damping ratio? Again, kind of more on the physical side of things. You need to use a little bit of math here, though. Any ideas? Yeah, we're going to do that in a second, but I'm looking for a more physical explanation for it. So it's relating to that. You're on the right track. We're going to go through the equation later on, but kind of like verbally explain it to me. I don't need specific letters or numbers. I need maybe something over something. How about that, since it's a ratio? Not quite. It's going to depend. It can relate to that in certain circumstances, but not always. It's a ratio. So ratio of what over what? Damping, because again, it's general. It's not just for mass spring dampers. Damping in the system over what? Maybe the critical damping, right? Critical damping value. Right. Okay. So we'll get back to that in just a second here. But first, I want to cover something that I've noticed people have mistakes for. All right. I give you a transfer function that looks like this. And I say, tell me what zeta and omega n are, right? How do we figure out what those two values are? Don't look at the numerator. I only want to talk about the denominator here. So how do you determine omega n and zeta, damping ratio, natural frequency, if I give you a transfer function like this? match the coefficients, right? So for our denominator, right, let's get that characteristic equation, s squared plus as plus b squared in this case, right? That would be equal to 0, right? Or s squared plus 2 zeta omega ns plus omega n squared. Looks nice and neat in this case, right? So we can obviously see these two should be equal to each other, and these two should be equal to each other. Right? So omega n squared or omega n will be equal to technically plus or minus b. We usually go with the positive one for frequency. It really doesn't matter if it's positive or negative, but typically we just say natural frequency is the positive value for this, right? Then 2 zeta omega n is equal to a. And so we can combine these two together here and solve for what zeta should end up being, right? Which in this case, I think it would be a over 2b, right? Now, what happens if I had the number 2 here? Does that work anymore? Can we just equate these coefficients directly? No, why not? Or what would you need to do to be able to solve for omega n and zeta? Divide by 2, right? So you'd have to do this, right? And then you can equate them. The coefficients in front, both are 1 in this case, right? These need to be equal to each other. If they're not, you're going to get the wrong values for zeta and omega, and I've seen that happen so many times. So I want to just try and kill that issue right now. Okay? All right. We can also solve for our poles with this form, right? So s squared plus 2 zeta omega ns plus omega n squared is equal to 0, right? And using the quadratic formula, we would end up with 2 poles because it's a second order system, right? Where there'd be a bunch of different forms of what it could be. I'm not going to go through all of them here, but you guys can go through and practice the math a little bit on your own. But what you could end up getting, I would say there's like, maybe let's go with these two, because I think they're pretty common. We'd end up with zeta omega n plus or minus omega n squared, zeta squared minus 1, or the same thing, plus or minus, if the stuff inside here is a negative number, we can take out our imaginary value j, and have it look like that, right? I'm not going to go through all the proofs and not even proof, right? Just the algebra to get this right. But this is a different form that we could get our poles if we know what zeta and omega n are, right? Because we're going to talk a lot in this class in terms of not just our poles, but zeta and omega n here. We're going to interchange them quite a bit. And then the last thing I want to cover here before we do some examples is something that somebody else touched on. We can use these to determine the second order system type. Just using that damping ratio, right? So last time we had our chart where we had undamped, underdamped, critically damped, and overdamped, right? And we talked about where the poles existed, right, to determine what form it is. This time, our identifier is just going to be the damping ratio. So maybe let's start with overdamped. We'll start at the bottom and go back up. What values do you think the damping ratio would be for an overdamped system? Greater than 1, right? What about critically damped? Can you say a little bit louder? Right? It's equal to 1, right? That's what the damping ratio is, right? If a damping ratio is 1, that means its ratio of its damping value or its coefficient over the critical damping one, the one that would make it a critically damped system, is equal to 1. They're the same thing, right? What about underdamped? Less than 1? And that's an important caveat there. It's greater than 0. Good catch, right? What about undamped? That's equal to 0. All right? Undamped, there's no damping in the system. The damping ratio would obviously be 0 in that case. What happens if a damping ratio is negative? What does that mean? Right? So it's like it's an unstable system, right? We would just categorize that as unstable. We really don't deal with negative damping ratios, right? It doesn't make any physical sense, right? But who knows? Maybe if you design a controller very poorly, you would end up with that case, right? So it'd be unstable, which we're going to talk about next week. Okay. All right. So just a few quick examples here. I want you to just determine the natural frequency and damping ratio. So let's have this first one. Let's have the folks online do this one, where we have S plus 20 over S squared plus 5 times S plus 400. Tell me what our natural frequency and damping ratio end up being there. And then for the folks in class, I'll give you the harder one, is 1 over 3 S squared plus 180 times S plus 900. All right, so tell me what omega n is and what our damping ratio is. You might as well tell us what the system type is too, for a second order system. Pretty basic, just something quick to warm up with here. Make sure you guys all understand this. So, number 1 here, I would just say natural frequency is 20, right? Square root of 400, we usually just go with the positive root for natural frequency specifically. Right, because a sinusoid at a frequency of 20 or negative 20 is still at the oscillating at the same frequency. Just the sign would change. What do you guys get for a natural frequency for 2? You guys talk so quietly. Come on. Was it? Is that right? What is that? Square root of 300, right? That's what we're going for here. In this case, I would just leave it that way. But if you want to, you can crunch it out. Sometimes we'll need to. 17.3. Okay, good. And then for our damping ratio, right? What's our damping ratio? So for problem number 1/8, 5/40.125. Right? What is it for problem number 2 here? Was it? Square root of 3? Is that what you guys got? 6/√3. Show of hands, how many people got this? Zeta and omega n. All right, this is pretty basic algebra here, guys. So you need to be able to do this pretty quickly here, right? 3s² plus 180 times s plus 900 is equal to 0, right? We need to divide by 3, right? And then it's just a matter of setting this equal to that standard or generalized second order equation. Right? Omega n squared is equal to 300. So omega n is the square root of 300. This one, sure, maybe it's a little bit more difficult. 60 over is equal to 2 zeta omega n. So 30 is equal to zeta square root of 300, right? 30 over square root of 300, whatever that number that comes out to be, right? So 30 divided by 17 point something, right? So for our first system, was that undamped, overdamped, critically damped, underdamped, or unstable? This is underdamped, right? What about that second system? This is overdamped. This number comes out to be, I think it's like 1.7, something like that, 1.73, ... All right. Quick review on how to get our damping ratio and natural frequency if we have our transfer function already. Okay, any questions on that? If not, let's move on to specifically talking about underdamped system characterization. We're going to spend a good deal in this class, especially towards the end, focusing on underdamped systems. Right. So for this part, we're going to study second order underdamped systems with a step response. Very often, when we're going to talk about these systems, well, especially when we get to control, we're typically analyzing them with respect to step responses here. That's like kind of the baseline that we tend to look at. All right. If not, it's free response. So our transfer function output over our control input will be that same form that we had before, where our input is 1/s, right? And specifically our damping ratio is going to be between 0 and 1 here. All right. The solution for this we can do with inverse Laplace transforms, right? I'm not going to go through that procedure. It could take a little bit of time. It's not really what this class is about for today. But if we went through and did an inverse Laplace transform for this to get y as a function of time, we would end up with 1 minus an exponential with negative zeta omega nt up here times cosine of omega n square root of 1 minus zeta squared, all of that times t, minus a phase angle phi here where that is going to be, this is a complicated part, our arctangent of zeta over the square root of 1 minus zeta squared. We don't have to worry too much about that piece at this stage yet. Right? But if we put in a step response for an underdamped system, what happens? What happens to this, right? We're going to have some oscillations, right? A cosine, right? Multiplied by an exponential. So those oscillations are going to decay over time, right? And we're eventually going to approach a value of 1 when our transient part dies out, right? It's going to look something, where's my figure? Like this. Let's make this a little bit bigger here. Right? It's going to look like this. For different damping ratios, it's going to look a little bit differently from one to the other. And this is from that nice textbook, specifically the 6th edition, but I'm going to bet that the 8th edition would have the same figure in it, if not a very, very close one. It just may have a different figure number for it. Right? So what do we see? We see our oscillations due to the cosine, right? But they decay over time. That's due to the exponential. And we have a steady state value due to that step response, right? The forced and free poles of our system, or free and forced, I should say, poles of our system, all working together to give us this total response here. So with that zeta value there that we have, right? Let's look at a pattern of how zeta's value impacts this system, right? So what happens when we have a lower damping ratio? What can you guys glean from that? More oscillations, right? Why does that make sense physically? What do you guys think? Why do we have more oscillations? But why? I think he was touching on it. Right? I'm talking physically. There's not as much damping, right? So it takes longer to dissipate energy, right? Our mass and our spring, right? If we have a damper in there, right? The mass and the spring are exchanging kinetic and potential energy, right? They're exchanging that form of energy. The damper is very slowly dissipating that, turning it into heat and throwing it away. But it takes a long time. So it bounces back and forth very slowly, getting to that steady state when it dissipates all that energy from our system. Right? Okay. Less overshoot. That's something else that we can see here, right? Specifically, with less overshoot, if we have more damping, right? And actually, if zeta is about above 0.7, right? What happens in that case? It looks like we don't have like a whole bunch of oscillations back and forth, right? You see that 0.8 case? It goes over 1, but then it doesn't go back under 1 after that, right? This guy right here goes up a little and then it flattens out, right? So if zeta is greater than 0.7, we don't have multiple back and forth around the steady state value. Right, that 0.707 is the actual number for it. That'll come into play a little bit later, right? That is for, I think that's the fastest response that you could possibly get with a second order system to get to steady state. All right, so with first and second order systems, right, we introduced, or with first order systems, I should say, we introduced a new handful of parameters, right? What were they? How do we describe our first order systems? What parameters? You guys remember that like case study that we did where it's like, I give you a set of data and I say parameterize our system, figure out what the values are. What did we use to figure that out? This is gonna be on the exam. It's on the homework too, right? What parameters are related to a first order system? What was that? Time constant, right? First order system. We had our time constant. What else did we have? The poles, right? Poles are always going to be true for all of these. But yeah, if we wanted to say the poles or pole for a first order system, what else? What was it? Rise time, that's for second order system, right? Or no, we did talk about it for first order system. Rise time, the one I like the least, but yeah, that's one of them. What's one I like more than that? I talked a little bit more about it. Maybe in the homework. Settling time. Right? Maybe you also want to throw in, I don't know, steady state value here, but that's again true for everything. For a step response. Right. So let's define similar plus new parameters to describe an underdamped second order system. All right, so we're going to be working with this equation here. Right, this will probably tell us some parameters, right? Specifically for a step response, again, is what I want to focus on. So maybe I'll just write it down here. For a step response, right? We had y was equal to 1 minus e, the negative zeta, omega nt cosine omega n 1 minus zeta squared t minus phi, and phi has a bunch of zetas in it. All right, so let's talk about how to characterize this, right? What are some maybe terms that we could group together here to get something, you know, some new parameters, some that may be relevant for an underdamped second order system, right? How about we start with the frequency of that cosine wave that we have there, right? Does anybody know the name of that? If we were to group all those terms together. What is omega n 1 minus zeta squared? Anybody know what that's called? Take a guess, right? Probably going to have something to do with those two terms that we have in there, right? So there's a damping ratio, there's a natural frequency, right? This isn't natural frequency. Damp frequency or damp natural frequency? Damped natural frequency. That's our first term here, omega d. We don't always use it, but it can be relevant at times here. That is our frequency that the sinusoidal part is moving at, right? So that's one parameter that would describe the system here, right? Frequency of the sinusoidal part of the response. Right? That's one thing. Okay. So let's move on from our cosine or sine, right? Let's maybe talk about that exponential, right? I want to define a time constant for an underdamped second order system. I'm still going to use tau for it, but any ideas what that time constant would be? Before, it was a negative inverse of our pole, right? It's not going to quite be this way, right? Because we have two poles in this case. What do we think? Just based off of this equation, what terms may be relevant Well, if we don't have a zero, then, how could we define that, right? You mean origin, closer to the origin? Not quite here. You're along the right lines of thinking. You're getting there. Inverse of the time step. What's the time step here, though? Time steps are for discrete time systems, right? The thing that's multiplied by the exponential, right? Remember, our time constant from the first order system was e to the t or negative t over tau, right? So maybe we can get an e to the negative t over tau in this case as well. So exactly, our time constant here would be 1 over zeta omega n, right? That is the negative inverse of the thing in the exponential here, right? It is the real part of our pole, right? They both have the same real part for an underdamped system, right? So it's not one versus the other because they both have the same real part. It's a real part of our pole here, right? We sometimes write this as sigma d here. This is sometimes they call it the exponential damping frequency. I don't really call it that, but that is a term that's been used for it. So that's our time constant. What about a settling time then? Just give me an approximation. How long does it take for all these oscillations to kind of die out and we reach approximately that value of 1? All right, what do we think? What did settling time relate to last time for a first order system? What? 4 times tau? In this case, we're going to approximate it as the same exact thing. For an underdamped second order system, our settling time T of S is just going to be 4 tau again, right? For overdamped, it may be slightly different. But for underdamped, which is one we're going to focus on a lot here, the amount of time it takes for our oscillations to die down is 4 times tau here. Again, relating to our time constant, right? We can get a rise time as well, as somebody mentioned here. And I am going to say, refer to textbook because it is numerically determined, right? There is no analytical solution for it where we get something nice and clean like this, right? Depends on what zeta and omega n are. You end up with a table of data. Typically, I'm not going to focus on that too much. If I do, I'll probably provide you the data that you would need for the rise time. Right? Relevant for some systems, but we won't focus on it too much today. All right. These are very similar to our parameters that we had earlier for our first order system, right? Now for an underdamped system, I want to just introduce a few more beyond these. These are essentially going to be different design criteria when we develop our controllers. Right, so I'm just going to plot y versus time here, where we have a steady state. Right, this is our y steady state value here. And then let's say step response, underdamped system. We have a response. It looks something like this. So zeta is going to be probably under 0.707 here. All right. So you guys have probably seen this figure before here, right? We can say our settling time, that'd be about here, right? We can identify where plus or minus 2% we're staying within our bounds, right? But I want to introduce 2 more parameters. The first one is here, and we've actually talked about them a bit already. Right? This is MP. Right? That is our max overshoot. Or max percent overshoot is what I tend to focus on. And then TP is our peak time, the time at which our max percent overshoot happens, right? These may be things that we want to design as we move in the class. I'll tell you, max percent overshoot, we're absolutely going to design a lot of things with respect to that. All right, so max overshoot. All right, I'm not going to go through the proof of it, but MP will be equal to the max value of Y minus the value of Y at its steady state, right? And if it was a mass spring damper, we'd get 1 over some sort of constant here times E, the negative pi, zeta, over square root of 1 minus zeta squared, right? What I think is a little bit more useful is to normalize it and to make it max percent overshoot here, where we're going to divide this by the steady state value, right? And multiply it by 100. Right, we're going to use this one quite often. Right, so our max percent overshoot is E to the negative pi zeta over the square root of 1 minus zeta squared, right? Max percent overshoot is only a function of our damping ratio. Right? You design a system to have a specific max percent overshoot, you're designing it to have a specific damping ratio. Right? And there is a relationship between these two, where zeta, we could solve this in reverse for zeta. And so if we have a max percent overshoot, we can work our way backwards and solve for zeta with that value. Involves using the natural log, but it's this formula here. Probably one of the most common formulas we're going to use in this class, and that's probably why exam number 2, I'll probably need to let you guys have the calculators. Because exam number 1, we don't need to do any calculations like this. Exam number 2, that almost certainly will come up. If not, then on the final exam for sure. This will be a very common equation that we're going to use here. All right, the relationship between our damping ratio and our max percent overshoot. Our peak time, so this is percent overshoot or max percent overshoot. Our peak time T of P is going to be pi over omega n square root of 1 minus zeta squared. But we already have that term here before. Peak time is pi over omega d. Right? Found by looking at that curve, figuring out where the peak and valley is, the derivative is going to be 0 at those points, and then solving backwards to get time. Right? So we can find the specific instance in time. It's related to essentially the oscillation of that cosine wave of when we're going to hit that peak. Okay? Any questions on this? Super, super important formula here. Going to use it a lot. This one too. That I would say actually this one even more so. We're going to use. Any questions? Yes. So I always try and operate in terms of radians, and then there will be a certain point in this class where using degrees is a little bit easier graphically, but it's probably good to always be thinking in terms of radians whenever we have like an equation and stuff like that. So that's what I would recommend here. Just be very careful about that. Yeah, it's implied here that I'm always dealing with radians per seconds for natural frequencies. Okay. Any other questions? All right, so let's wrap this up. Very similar to how we did it with our first order systems, right? I tried to end that first order system class by talking about why that stuff could be valuable. And one thing was model fitting or parameterization. I think I used an example of a battery, right? And I'd have an assumption for what its model would be, but I don't know what its parameters were, right? I looked at the data, I used these equations, and I figured out what the parameters of that battery would be. Now let's say instead we have, I don't know, like a very, very simple like robot that's modeled as a second order system. Right? We're going to assume the form where we have no zeros, only poles. Right? Like, let's say like it's a little like robot car or something like that. We have some sort of input, we have some sort of output, probably like velocity relating to it or something like that, maybe position. It's modeled as a second order system, right? How do we figure out the parameters for that model? Right? Same thing as last time. What did we do last time? How did we talk about it? I give you guys a little RC car, and I say get a second order transfer function to represent that system. What? Yeah, let's assume we can measure position versus time, right? Or whatever our output would be. Okay. But we need to do something in order to get data versus time. It's just going to sit there on its own, right? So what do? Stare at it blankly, like a lot of you guys have for this class. A lot of you guys have participated, but. Okay, what kind of input? Like, do we just turn it on and off? Constant, ramp it up, parabolic input? Well, sure. I mean, it'd be, you have a remote, right? And you're just going to press forward on it. It's a throttle, right? Let's say. Right, and you're going to measure position versus time. What do you set that throttle to be? And it will change a voltage internally, blah, 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 all that stuff. I think if you have a control for that, right, you're assuming that you have some sort of feedback law where it'll set itself to 20 miles per hour, right? But the RC car is just a throttle. It's 0 to 1, right? You're on the right track. Set it at a value, right? Let's say 1 for now. You can set it at 0.5. Set it at a constant value, right? And see what happens. Measure that data versus time. Okay. And it's a very weird RC car because it oscillates. I think we said we were talking about position before. Maybe we should talk about in terms of velocity instead. Because if we set it to a constant, its position goes back and forth, that'd look kind of weird, right? So let's say its velocity does something like this. All right. Okay. So now we have some data to work with, right? And I've chosen a few select points here, right? I want to figure out what omega n is. I want to figure out what zeta is. Right? So we have done essentially a step response, right? And we've gotten data for a step response. What is omega n? And what is zeta, right? That would parameterize our model. Ideas. What do we do with this data now? Okay, good. So zeta, right, is related to our max percent overshoot or max overshoot here, right? We had that formula. ln 100 over max percent over pi squared plus ln 100 over max percent. I think that there should be a squared on this and then a square root over all of this, I believe. All right. What's our max percent overshoot from this graph? Is that percentage? So what does it end up being? You're good. You participated a lot today. %44%, right? The steady state value is 1. This is 1.44, right? So we're 44% over. Okay. So what do we end up with as our damping ratio in this case? I think we're running short on time here. So you guys should go through and double check to make sure you know how to calculate this properly. Sometimes people use log base 10 here instead by accident, or if they get the square root or something like that. I believe the number should come out to be about 2.25 here. So that's our damping ratio for our system. We found one of our parameters. Now, how do we figure out what omega n is? Peak time? Okay. So our peak time formula, TP, was equal to pi over omega d, right? Or pi over omega n square root of 1 minus zeta squared, right? Okay, and let's solve. What's our peak time in this graph? It's 0.47368, whatever, blah, 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 blah. 0.47, let's just go with for now. 0.474, right? We know what zeta is. Let's solve for omega n. All right, what do we get for omega n? .8. Yeah, I think 6.85, something like that. Okay, good. Was this the only way that we could have gotten omega n here? Right? Was there any other formula we could have used? But we don't have the original transfer function. That's what we're getting here, right? How else could we have done this instead of peak time? Use the settling time, which is related to the time constant here, right? So if we were to rearrange that settling time formula, 4 over zeta T of S, right? Our settling time is about 2.05 seconds here, right? We crunch this out and we get 7.77 for omega n. Which one's right? I'd say both of them are approximate, right? The true answer is probably somewhere in between these two. I think the true answer is actually 7 in this case, right? Those are both formulas are approximations, right? You need to use your judgment to figure out which one will be best. All right, that is it for today, folks.